From space, we can see how the Earth's atmosphere is only a thin gaseous layer. Even then, only the lowest part contains most of the weather systems. Weather is constantly changing, and our knowledge of the weather has come from years of observing and recording weather information. One such recording station is at Perth Airport. Tucked well away from the aeroplanes, it goes about the routine business of collecting weather data. Every 6 hours, a hydrogen-filled weather balloon is released. Attached to the balloon is a reflector, allowing it to be tracked by radar. And twice a day, balloons also carry a radio sonde package, which can send back extra information by its own radio signal. A balloon released with a reflector alone can be tracked for height and direction, which shows how the winds are blowing at various heights. The radio sonde can measure temperature, humidity and pressure. These balloons have been tracked up to the enormous height of 27,000 metres, sending back their information all the way until the balloon swells so much in the low pressures up there that it bursts and falls back to the ground. Inside, the radar screen shows the balloon's position and the information is fed into a computer. This radar is also used to detect rain. Falling drops of water reflect the radar signals directly, so the radar dish automatically scans at different levels throughout the day, keeping an eye out for rain squalls. Then it's time to take the readings for the day. As he walks out to the instrument enclosure, the meteorologist takes note of the clouds he sees. In this simple visual study, he notices the amount of cloud coverage as well as the type of clouds at low, mid and high levels. Today it's mostly high-level cirrus clouds. He also assesses the surface visibility in all directions. To ensure that measurements at all weather stations can be accurately compared, the instruments are kept in a standard box-like structure called a Stevenson screen. Inside here we can get the day's maximum and minimum temperatures. These are wet and dry bulb thermometers which tell about humidity, which is the amount of water vapour in the air. The rain gauge is checked. Its position is important. Not only does it have to be in the open, but it must be well away from the buildings and trees. The enclosure houses several other measuring devices. This one is for measuring airborne radiation or radioactive particles. This one measures the ultraviolet and other radiation from the sun. And this one measures global radiation, which is the amount of solar radiation reaching the surface. Back inside, the all-important pressure or barometric reading is taken. And over on the other side of the building is another global radiation recorder. It's housed in this special dome. What everyone wants to know about these days is what's happening to the ozone layer. This instrument finds out by measuring ultraviolet radiation from the sun. It's called a Dobson spectrophotometer. The ozone absorbs different types of ultraviolet light at different rates. So by comparing two wavelengths of light, the amount of ozone can be calculated. This particular photometer is very important because it's one of only 8 automated ozone recorders in the world. Altogether, these instruments give a good picture of the weather. When linked with data from across Australia and indeed the world, a reasonably accurate forecast can be made. This is the way many people think the weather is forecast. And maybe it is. Yep, looks like rain today. We have previously seen how information about the weather is collected at weather stations. Readings of temperature, rainfall, winds and the like are taken every day around the state. But what happens to this information? How How is it used in weather forecasting? Well, all of the information comes into this room and is processed by these computers here at the WA Bureau of Meteorology, or as it's commonly called, the Weather Bureau. With me today is Malcolm Young.
Good morning, Jeff.
A very impressive array of computers.
It certainly is. We're handling a lot of information here. Around every 3 hours we get information from up to 150 stations, from ships and radios from the high seas, from outback stations. They phone in their reports. From all our other stations closer to the coast, we get computer input, and all this data comes into our main computer bank here.
And what do you do with this data?
Well, this is just the start of it, Jeff. We process it from here, and the first thing we've got to do is to make sure it's okay.
And where's that done?
We do that in our quality control section. Come with me.
Okay. Now, there's a lot of data in there, Malcolm. Do you ever get any weird reports like snow in Port Hedland?
We get them, Jeff, but we don't believe them, and neither does the computer. If a funny report like that arrives, the computer alerts us on a special machine, prints out the funny report, we get the information and we get back to the observer and we double check. We ring them and make sure the report's accurate and put the correct information back in the computer.
So the data's come in, we've checked it, then in what form do we get it from here?
The computer's going to present it for the forecaster to use now. We've looked at machinery now, we're going to look at data, and it's going to plot it on a high-speed plotter for him to look at. What you can see here, Jeff, is the high-speed plotter is plotting all this data from all the stations in Western Australia onto this chart. Each geographical location has its weather data plotted. This morning at Carnarvon, for instance, the temperature's 17, there's a light southerly wind and the pressure's 1,018 hectopascals. So all that data is plotted for each station around the state.
And how often is one of these charts produced?
We do them every 3 hours, and that gives us a really good chance to have an accurate watch on the weather so that nothing happens that we don't know about.
And once it's finished plotting, where does this chart go from there?
Well, we'll take it to the meteorologist. He'll start drawing today's picture of today's weather on that by hand. Right, Jeff, the computer's finished plotting our chart. I'm going to take you into the Regional Forecasting Centre and we're going to go through the process of analysing this. This is where it all happens in Western Australia, the centre of forecasting. Many different areas operate here. We've got aviation, for instance, look after the aviation safety aspect of weather. In the centre of our whole forecasting section is the shift supervisor, and Graham coordinates the whole process and makes sure that all the forecasts are accurate and timely. Today we're going to give our chart to Linda to analyse. Linda's a public weather forecaster this morning, the duty meteorologist. Let's see what sort of job she can do with the chart this morning.
It's my job to draw the chart. A person draws the chart rather than a computer because we can deal with the detail required better than a computer can. We can locate, say, a cold front with more accuracy than a computer. We can also pick up any errors in the chart. Say if some of the pressure readings are too high or too low, we'll recognise that, but a computer won't. It will just try to draw the isobars as the numbers appear on the chart.
So where do we start in relation to drawing the chart?
Firstly, I'll look at all the previous charts to give me an idea of what mine's supposed to look like. Then I'll take the satellite picture and I'll locate the cold front or the other weather feature on here and then transfer it onto the chart. Then I'll find any extra ship observations we've got out here, put them onto the chart and basically start drawing.
Now this is a surface chart here. Now we all know that there's a lot more weather above the surface.
That's right. It's like a big river, the atmosphere. Lots of things are happening. Next time you're near a river that's flowing, watch the water. And that's a bit like what the air does. It comes together and it bubbles. The air comes together and it bubbles. Clouds form. And when that happens, it rains. All those sorts of things are happening all the time, and it's not just all on the surface. We've got to take account of that three-dimensional picture of the air above us when we make our forecast. So it's not easy. There's a lot of things going on there all at the same time. And to help us with that, we've got analyses, charts for all those different levels above the Earth's surface. We've got them on the wall over here. So let's have a look at this three-dimensional aspect, Jeff. Let's compare some of the charts for the surface and the upper levels. This morning's surface chart, when we look at the chart for 12,000 metres, there's no comparison between the two. There's a lot of different things going on up there compared to the surface. And it's the combination of that, the interaction, that we're trying to work out to forecast the weather. It's a complex process, and we've got to think about a lot of things as we do it.
That's right, there's a lot going on. And I've also noticed that this is a Melbourne chart, so you're not working in isolation here, are you?
No, we've got good communications, Jeff. We're in touch with the whole world with their weather charts. This is from Melbourne. We've got a chart here this morning from Darwin, which goes as far north as China with its analysis. So we've got a global weather watch system that works right around the world. Let me show you some products that we get from America. This 4-day chart, we call it, it forecasts what the weather map's going to look like for the next 4 days. America sends us that every day. We get one similar to that from Europe as well. This exchange of information around the globe is going on continuously, and we can't do without it. It helps us be accurate with our forecasts.
And why only 4 days?
Well, 4 days is about as good as we can get. So far, we haven't got the switch that gives us control of the weather. We don't like to forecast into a period that we're uncertain about. People make decisions on our forecast, and we want to help them make the right decisions. So we stick to 4 days. We can keep accurate within that period.
And what are some of the difficulties we have in forecasting our weather?
Well, particularly for Perth, I think the biggest thing is the big area of ocean that we've got to the west of us. You know, looking at your globe, there's a huge ocean area between Western Australia and South Africa. And that basically is where our weather comes from the west to the east. So we look at our weather chart here, and there's a big gap where there's no data. We've got to try and interpret the satellite photo, try and detect from that what the weather systems are looking like. And with just the odd ship report from out in the middle of the ocean, we've got to use that as the basis for our forecasts.
And one thing I've got to know before we leave is, does the Weather Bureau have a dartboard?
No, Jeffrey, we sold that. It wasn't worth it. We were much better than it was.
We know that the atmosphere and the weather is more than just what is seen at the surface. In fact, the atmosphere is usually regarded as extending up to 1,000 kilometres above the surface. The atmosphere is broken into a number of different layers based on the temperature and number and type of particles present. When talking weather, we are mainly concerned with the bottom layer, the troposphere. This layer extends up to 8 kilometres above the poles and up to 16 kilometres above the equator. It contains most of the mass of the atmosphere, most of the water vapour, and therefore most of the weather. Above the troposphere, the stratosphere does contain some high-level weather effects. Through information gathered by satellites and space shuttle programs, scientists are learning more about the upper atmospheric layers and conditions on Earth in general. There are many upper-level effects which, as such, don't appear on the surface weather chart. Tropical clouds, usually mid and upper-level clouds, are often seen streaming across the state, usually travelling against the direction of the wind shown and felt at the surface. You may have noticed that yourself, clouds moving against the wind, but where they are flowing with the wind. Such clouds often make conditions cooler or wetter than you would expect from the surface chart. Other features like troughs, fronts, highs and lows all extend above the surface. Blocking highs, strong high-pressure systems which often remain stationary for days in the Bight over Victoria or in the Tasman Sea, remain strong because they are fed from air from upper-level sources.